So, very good evening to all. So, today we are going to have a webinar on Microstrip patch antenna design using CST software. So, myself, Professor Jones, working as assistant professor. So, this webinar is split into two parts. In first part, we are going to have a small PPT presentation since most of the second year and third year students have been registered for this program. In that PPT, I will show you the some basics about the antennas and why we are in need of antennas, and now what is the present scenario in the antenna design. And after that, we totally goes into the CST design simulation studio presentation, right? So actually, we plan to conduct this webinar using WebEx, but fortunately, we have more than 1,500 registered participants. I can't able to accommodate in the WebEx, so we have a live stream now. So, what is an antenna? So, antenna. The first antenna has been have been created or invented by a German physicist called Hertz when he tried to prove the existence of the Maxwell theory. So he placed a dipole antenna at the focal point of the parabolic in order to transmit and receive the EM signals. So what is an antenna? So the antenna is a metallic apparatus which can able to transmit or send or receive the electromagnetic waves. In case of waveguide, it is a metallic device for radiating and receiving the radio waves. And the famous Balanis reported the antenna as a transactional structure which is placed between the free space and guiding structure, in between the free space and the guiding structure. So an antenna is an electrical device which can convert the electric current into radio waves and vice versa. Basically two types of antenna, one is transmitting and another one is receiving. In case of transmitting, it is able to radiate the electromagnetic radiation efficiently. In case of receiving antenna, it can able to efficiently receive the electromagnetic radiations. So what are the different types of antenna? Wire antenna, aperture antenna, array antenna, reflector antenna and lens antenna, and then the patch antenna. So in case of wire antenna, a simple copper wire of resonant length of lambda by 2, when it is properly energized, it can able to act as an antenna. Aperture antenna, the slot on such types of antennas comes into the aperture type. So then the array type, array is nothing but the similar elements are placed and fed with equal amplitude and equal phase, or equal amplitude and unequal phase, gives the array antennas. It is used to improve the gain on directivity of the antennas. And then the reflector antennas, the parabolic reflector, and lens antennas which are widely used in the radar applications. And then finally the patch antennas. These patch antennas is nothing but the microstrip patch which plays a key role in the miniaturization of all the wireless devices that we have now, right? So why antenna? So let us consider a scenario when there are two persons, they need to communicate but there is no wired communication between them, it is not possible. Then automatically the radio waves are the electromagnetic waves which is used to carry the communication signal from one end to the another end at the speed of light. So whenever the radio waves are going to play a key role in the communication, then automatically in order to transmit and receive the radio waves, the antennas are necessary. So what is the basic structure? So it may be a metallic conductor, or it may be a arrangement of conductors, metallic conductors, and they are electrically connected to the receiver and transmitter. So at the transmitter side, the transmitter will induce an oscillating current of electrons, so which will create an oscillating magnetic field around the antenna elements, while the charge of electrons also create an oscillating electric field, and this time varying field will move into the space as it moving as an electromagnetic field wave away from the antenna. And conversely, during the reception, the oscillating electric and magnetic field exert a force on the electrons in the antenna elements, which in turn it will create an oscillating current in the antennas. So this antennas can able to transmit equally in all directions, which is called as omnidirectional antenna, and it is when it is going to transmit in a particular direction, and it is called as directional antennas. There are two fields, one is near field and another one is far field. Usually the antenna characteristics or parameters are measured for far field. We are in need of far field parameter results. So the near field is nothing but when an antenna is enclosed by a smaller sphere, the region within the sphere is called as nearest field or personal field, or the region away from the apart from the near field, then it is called as the far field. Where it is used, so antennas are used in a system such as radio and television and broadcasting, and also it is used in point-to-point and radio communication, wireless LAN, radar and space, and mobile phones. These are the normal antenna application areas. So now in the current trend, this antennas has been designed for underwater and even through soil and rock for short distance communications. So this is the major antenna research area. Now it is in trend. Then I already told about the omnidirectional and directional antennas. So what is the radiation mechanism? So ideally, all the incident energy will be reflected back when it is open circuit. But practically a small portion of electromagnetic energy will escape as then that is it gets radiated, right? So the amount of escaped energy is very small when there is a impedance mismatch between the transmission and the surrounding space. In order to match that, the open circuit must be enlarged. So because of this enlargement, the coupling between the transmission line and the free space will be improved, and as a result the radiation efficiency will be increased, right? So now we are slowly moving into the microstrip antenna. So this is the fabricated antennas which is there. So it is also called as patch antenna. So one of the most useful antenna at microwave frequency. It is used at microwave frequency, that is frequency above 1 GHz. So it usually consists of a metal patch on top of the ground dielectric substrate. That is, the dielectric is sandwiched between the patch and the ground. So variety of shapes are there. So this is a simple fabricated antenna. Here it is a patch, and this is the SMA connector through which the input has been given. So it is the coax feeding. This is microstrip feeding, and this is the coax feeding. So microstrip feeding is in line with the field line, and coax feed is given from the bottom of the antenna, that is through the ground, and through the dielectric it reaches the patch. So I will explain this two types of feed in the later stage. The this area, this is called as the radiating element or the patch, has different variety of shapes. These are the sum of the shapes: rectangle, square, circular, annular, elliptical and triangle. So these are the common shape, and for all these shapes we have the common formula for calculating the resonant frequency, and the length and width of the each shapes can be easily found out with the help of the equation, and from that equation we can able to design it. And regarding history, it is first invented by Bob Munson in 1972, and it became popular in the 1970s. So what is the advantage of microstrip antenna? So it is low profile. What is low profile means? It is conformal in shape. So that is, it is flexible to any surface, that is conform to any surface, and it is easily fabricated with the help of etching and photolithography process, and it can be easily fed with the help of coaxial cable type or microstrip line, and variety of feeding techniques has been evolved in the literature, and easy to incorporate with other micro circuit elements, that is the microwave integrated circuits, and integrate with the system. And the patterns are somewhat hemispherical and moderate directivity, which can be about 6 to 8 dB, and easy to use in the array in order to increase this directivity level. But the major disadvantages, it can able to produce up to 5 dB of gain. So the major disadvantages, the first disadvantage is the low bandwidth, and the efficiency is lower when compared with the other type of antenna because of the conductive dielectric losses and surface wave losses. And another major disadvantage is it can be operated with the microwave frequency. It can be operated above the microwave frequency, and it cannot able to handle the extremely large amount of power since it is use a dielectric. Because of that, the dielectric breakdown has been done. So this is a simple rectangular patch. So here it is the ground, and this is the substrate, and this is the patch. So the length and width, the width of the patch should be typically 1.5 of the length of the patch in order to avoid the 0-2 mode problems. And this is the circular patch, and instead of a rectangular shape of patch, here we are going to have a circular shape of radius A, and the location of this circular feed determines the current flow and hence the polarization of the antenna. So what are the different feeding methods? The first feeding method is the coaxial feed. So in this we know that the coaxial cable is going to have two conductors, one is the outer conductor and another one is the inner conductor. In this, the outer conductor will be connected to the ground and the inner conductor will be penetrated to the ground through the dielectric and reaches the radiating element, that is the patch. So when you are going to have a feed position at y equal to w by 2, then it will minimize the higher order mode and cross polarization problems, which is usually available in the microstrip patch antennas. And next one is the insert feed. So it is a simple feed, it allows the planar feeding. So we are going to have a cut and then the microstrip line has been given in order to give the feed. So it is easily converted. This type of feeding help us to easily convert a single unit into an array, and it can able to easily obtain the input match. And the major disadvantage is the deep notches have some distortion produced in the patch current and the radiation pattern. And next one is the proximity coupled feed. So here the microstrip line is penetrated through the substrate, and because of the coupling between this patch and the microstrip line, the radiation has been occurred. So the major disadvantage is it requires the multi-layer fabrication. It is quite difficult. The advantage is the line radiation is very low when compared to the microstrip feed line, and it can also able to achieve a higher bandwidth when compared to the microstrip and coaxial feeding. And gap couple, here the gap is major important while fabrication. If the gap is not properly maintained during fabrication, then the patch do not work correctly. So it allows planar feeding, and it high edge impedance can also be matched with the help of gap, and it requires accurate gap fabrication, as you know. Right. So these are some of the findings that I come across while doing my research. So the two major important thing in the microstrip antenna is to improve the gain and is to improve the bandwidth. To improve the gain, some of the techniques has been identified. So these are already available in the literature. Just I give an insight to you. To improve the gain, the effective area of the antenna should be increased. So this effective area can be increased with the help of parasitic patches and meandering of the edges, and we can also using the EBG structures, electronic band gap structures. So this meandering will be enhancing the surface area through projection and serration on the edges. And second one is cavity backed antenna can be used, and EBG and metamaterials are now used to improve the gain. And in order to increase the bandwidth, we have to increase the substrate height, or we can make use of the partial grounds, or include the round shapes, or include the slots, or include the DRA, dielectric resonator antennas. So when we are going to decrease the relative permittivity, both the length and width will be increasing. So because of the length and width is going to increase, the fringing fields will increase, and aperture area also increase, and hence both the bandwidth and gain will be increased when we are going to decrease the relative permittivity. In case of increasing this relative permittivity, that is the material we are used, dielectric material we are going to use, it will decrease size of the antenna decrease for the same frequency, and hence the gain decreases, but the half power beam width gets increases. So these are some of the findings. So these are the equations used to design the rectangular microstrip patch antenna. So here W, which is equal to C divided by 2 F naught root of epsilon r plus 1 divided by 2. This F naught is your resonating frequency, 3 is the 3 into 10 power 8, and epsilon r is based on the dielectric material you are going to use. From that you can able to find out the W. Then you have to use this W here, and the H is the substrate height. By solving this you can able to find out the epsilon E, and then you can just find out LE and WE using del L by calculating the del L. So this is the equation by which the rectangular microstrip patch antenna can be designed. The fundamental mode will be equal to TM10 mode. And for the circular patch antenna, the design equation, the resonant frequency is KNM C divided by 2 pi AE root of epsilon E, where KNM is the mode equivalent number, so which is for each and every mode the mode equivalent number has been given. And the fundamental frequency, that is the basic design equation to find out the radius is given by this formula. So you have to, when you are going to choose a coaxial cable, then you have to choose the feed point from 0.8 to 0.5A, which can able to have a very good working. And then the equilateral triangle, so here also you have to find out the side length, so which can be used with the help of this formula. The fundamental mode is TM10 mode. The fundamental mode is TM10 mode. And this is the fabricated design for some of the arrays. So you can clearly see the microstrip feeding and quarter wave microstrip feeding has been used widely in order to convert it to array, since it is easily designed and fabricated. And then the implantable device, so up to which we have seen some basic concept about the microstrip patch as well as some feeding techniques. Now what are the current trends for the microstrip patch? The first one is the implantable device. The device which is implanted inside our body is nothing but the implantable device. So two main functions, one is applying therapy and second one is the monitoring the relevant parameters. So for both this we have to the implantable device will be available inside our body, then automatically through wireless communication only we are going to initialize the devices, then automatically the antenna comes into the role. So here a paper which is already designed by someone. So here two spiral antennas has been used. So the substrate used is alumina substrate. So it is used for the ISM band 2.41 GHz. So here it is based on the CPW, that is in microstrip patch antenna we have the ground at the bottom, but in CPW the ground, the copper thing the copper plates which is available at the adjacent side of the feed is going to act as the ground. So it is the difference between the CPW and the microstrip patch antenna, right? So in the designing while designing an antenna for an ISM band or implantable device, we have to create and fragment a structure, and then we have to analyze the design in the any CST Studio or HFSS or any simulation softwares, right? So in this way you have to design first the muscle and second the antenna, fat and skin layer. So in CST you can create a box and then you can assign that box as a muscle, and that muscle can be assigned with the help of the permittivity and the permeability conductivity value, so which is equal to 5.27 and 1.73 respectively. So by assigning that these values, the box will be able to behave like a muscle, and after that you have to design that, and after that a fat layer and skin layer, then you have to analyze it using the simulation software. This is the simulator and the experimental result presented in that paper, right? So this is the experimental setup, and this is the pictorial representation of what we have seen, and this is the fabricated antenna. So in this MICS band as well as ISM band has been available with the help of coaxial cable, and the sorting pin is used along with the superstrate, right? So normal materials cannot be utilized for ISM band application or medical application. So the materials should be biocompatible in nature, since we are going to implant the device inside our body. So these are some of the materials, substrates used for the medical applications or implantable antenna designs. You can note down this, right? So these are some of the fabricated antennas for the ISM band, right? So in the medical application there are two methods has been utilized. The first method, when you are going to design an antenna for the medical application, you have to, there are two methods have been implemented. The first method you have to use the biocompatible substrate or superstrate and biocompatible metals in your design. So that is the first method. In the second method, you can able to use a ordinary substrate or superstrate, and then you have to go with a biocompatible coating. You have to make use of the biocompatible coating. So these are the two methods by which you can able to design an antenna for the compatible or implantable devices. Right. So this is the CST software. Uh, so in the simulation, the antenna which is designed is placed near the chest, and then we can able to analyze the what is the specific absorption rate, that is the amount of energy absorbed by the body. So we can just place the designed antenna anywhere in your body. We have a good subvoxel human body model in the CST, and we can place there, and we can able to analyze the specific absorption rate for 1 gram or 10 gram distribution. And we can another important thing is we can also able to analyze the internal organs also, and this is the simulated experimental setup in which a rat is used. And here the radiation pattern can also be identified. What is the how the radiation pattern is gained is of a PIFA antenna in a human model. So it is in HFSS, ANSYS male human body model. It is a HFSS simulation result. And here you can able to see the what is the SAR, local SAR distribution on the upper male body. So here the internal organs can be easily verified with the help of SAR at 402 MHz. Right. And next one is the wearable textile and flexible antennas. So these are the antennas which is widely used in the military application and some personal components. So these antennas are integrated into your clothes and human bodies. That is, the antennas are presented in your waistcoat. So you need not have to carry a special device for your communication, right? So many conducting threads are available in Flipkart and Amazon. So you can buy that, and with the help of your embroidery skills, you can design the antenna by embroidering in a fabric. So these are some of the examples of the wearable antennas. And next one is the printing conductive polymers. Flexible antennas are available here. A flexible paper krypton substrates are available, and paper substrates are available. We can just print and use which leads to the flexible devices which are yet to come. And next one is the metamaterials. These metamaterials are the materials which are man-made and which do not have a natural property, that is it is going to have a unnatural property, that is it is going to have a negative permeability, and because of that the negative refractive index has been evolved. So this is the negative double negative medium given by the Smith. So this is the MIC component. So it is Microstrip CRLS implementation. Here this part, black part, is going to act as the inductance, and the gap between these parts is going to act as a capacitance, LNC component. And various split ring resonators are available. So the first one is multiple split ring resonator, and second one is spiral resonator, and third one is the labyrinth resonator. In case of multiple split ring resonators, multiple rings are available, and there is a split in between the two rings are exactly opposite to each other. And here this split and the gap between the two rings is going to act as the capacitance, and this ring is going to act as inductance, LNC combination. And this is the spiral resonator. Here also the gap between the two rings is going to act as capacitance, and this copper material is going to act as the inductance. And this is the labyrinth resonator. Here it is similar to multiple split ring resonator, but only thing is it is going to have two split exactly opposite in the same ring, and in the next ring it is rotated by 45 degrees. The splits are rotated by 45 degrees. Right, split ring resonator. In this, two concentric rings which are separated by a gap, and both have splits at the opposite sides. So because of this, the magnetic resonance is induced by the splits at the ring and the gap between the two rings. The SRR behaves like a LNC, parallel LNC. The two rings are coupled by a strong capacitance, so which is caused by the gap between these two rings. This part is responsible for the capacitance. and the induced current will pass from one ring to another ring through the by means of the displacement current. And what are the parameters influencing the magnetic resonance? Origin of capacitance and inductance. Total capacitance arise from the splits and other from the gap between the two rings, and the inductance arise from the conducting rings. What is the effect of physical dimension on the resonant frequency? As the split width, that is the split width, if the split width increases, the capacitance decreases, and when the capacitance decreases, as the resonant frequency increases. And the gap distance, if the distance between the gap increases, the resonant frequency gets increases. If the metal width increases, the capacitance will be decreasing, and as a result the resonant frequency will be increases. If the additional capacitance is that, the capacitance will be increased and resonant frequency will be decreased. Right. What is the effect of variation in the number of splits? When you are going to have only one ring, then if we are going to increase the number of splits, then automatically the capacitance will be connected in series. So therefore automatically the capacitance decreases by the factor of 2. So whenever the capacitance decreases, automatically the resonant frequency gets increases. When we are going to make use of two rings, then the increase in increase in the number of splits automatically decreases the resonant frequency. For example, when you are going to make use of a single ring and design an antenna for 5 gigahertz, and you have to make that antenna to resonate at 5.2, then you can increase the number of splits, and then you can able to increase the resonant frequency. Right. Complementary split ring resonator, which is nothing but the dual of the SRR. So here you can able to see that the rings are surrounded by the air, and here you can able to see that the air is surrounded by the copper material, right? From the copper material a part is etched. So the performance of both the SRR and the CSRR is one and the same. Right. Some of the major other type of split ring resonator are non-bianotropic broadside couple. So these are some of the designs which can able to enhance the capacitance, and this is the spiral resonator. So the major advantage of using the spiral resonator is the electrical size can be reduced, and also either the capacitance or inductance can be enhanced. So these are various types of spiral resonator, and this is open split ring resonator. It is widely used to reduce the size by 20%, and the S-shaped resonator. So usually the SRR has the negative and permittivity and permeability, has both the negative permittivity and permeability, negative permeability and permittivity, but they do not overlap with each other. So in order to achieve that property, the S-shaped resonator has been built in, and omega shape. So in a C-shaped ring, the resonator 2 wires at the both ends has been introduced. So these are some of the multidisciplinary topics which can combine to have the body centric networks. So a slight introduction about the CST studio. So the entire design can be made from the touch screen to the photonics, from the static frequency to the terahertz frequency can be designed. These are some of the materials. Now the graphene and ferrites has been included in the CST studio. So, and another one is biological electromagnetics. So this biological electromagnetics which can able to reduce the SAR from 1 which can able to calculate the specific absorption rate, particularly 1 gram, 10 gram, and average SAR and whole body SAR can be easily calculated. The BioEM, biological electromagnetics, can be easily calculated, and these are some of the supported formats. A complete technology and methods to suit any task, automated processing result, get the output what you want. In a single click you can able to achieve the result what you want. So today we are going to design an antenna. So this is the antenna what we are going to design. It is a simple microstrip patch antenna. This is antenna A, and in the antenna A we are going to have a substrate, and we are going to have a feed line, and we are going to have a rectangular patch. At the back side of the substrate we are going to have a ground, full ground. And antenna B, that full ground is reduced to uh, half, that is 3 by 4. The length of the ground is 8, is calculated 8. And antenna C, we are going to cut a U shape, and this is the antenna D, we are going to include 2 rings. So this is what we are going to see in detail in this design. So based on the design equation what we have previously seen, I have arrived at the various values. These are some of the values. That is the WS is the width of the substrate, LS is the length of the substrate, and LG is the length of the ground, WF is the width of the feed, LF is the length of the feed, WP is the width of the patch, LP is the length of the patch, and W1 and L1 is the width and length of the square box from which we have to we are going to cut. And then 2 rings of radius R1 and R2 has been calculated with the help of SRR equation, and S is the split width, and D is the split width, and S is the thickness of the copper rings. So these are the design parameters, and these are the design parameters values. These are calculated with the help of the design equation what we have seen in the previous slides. So T is 0.035, which is the thickness of the copper, and H is the 1.6, which is the thickness of the substrate, the FR4 substrate what we are going to choose, right? So this is regarding the PPT, and now we can able to go to the CST Studio. So this is the icon. On single click you can have it. So this is similar to a Word document. Here a new document will be there, and click on create project, and you can able to view the entire window. So here you can able to see the application area. So this static and low frequency application, which is used for the low frequency transformer design, touchscreen design, static frequency, low frequency application, and microwave, RF and optical application can be viewed here, can be designed here, and EDA and electronics for the PCB and other electronic designings. And then EMC EMI application, which is nothing but the electromagnetic compatibility and electromagnetic interference simulation, and charge particle dynamics, which is used to design the microwave signal sources, right? So I am going to design an antenna, so I am going to choose the application area as microwave, RF and optical. So on clicking on that, you can able to arrive at the workflow diagram. Various workflows are available. The first one is antenna, and second one is circuits and components. When you are going to design a filter or waveguide or any RF circuits, related circuits and components, you have to go through this workflow. And then the radar cross section, biomedical SAR, that is the specific absorption rate and the exposure, and biomedical, regarding the biomedical experiments you have to go in this workflow. And optical related to the application related to optical, you have to make use of this, that is the terahertz frequencies. And the periodic structures, that is the FSS metamaterial unit cells, can be designed with the help of the periodic structures. And here it is the antenna. So I am going to choose the antenna and click on next. And here when you are going to choose the antenna as the workflow, then you can able to arrive, you can be able to view the multiple number of antennas, such as waveguide antenna, planar antenna, wire antenna, phased array, mobile reflector, dielectric resonant, and RFID. So based on your application, you have to choose that. Here I am going to choose a patch antenna, since I am going to design a Microstrip patch antenna, and click on next. So the CST itself recommend 3 different types of solvers. Usually choose on time domain, you can able to analyze. And then dimension and frequency, all the dimension I have calculated in mm, and so I am going to choose. If you calculated in centimeter, then you can choose anything, you can choose. And the frequency I am going to use is gigahertz, and click on next. So this is the important thing, you have to give the minimum frequency and the maximum frequency. So here the minimum frequency and maximum frequency I am going to represent it as 1 and 10. So since I am going to design an antenna in the wireless region between 2 to 5, so I have to analyze my antenna from 1 to 10 gigahertz. That is, your desired frequency should be inside the minimum frequency and the maximum frequency. And click on next, and then finish. So this is the design window. So this is the design window, you can able to clearly see. So this is the navigation 3 and this is the working field or working plane, and here the parameters can be identified and given, the parameter values can be given, and then here it is the progress. After the designing it, we have to simulate it and we can able to view the progress, and after that the message, after this message, after simulating, the messages will be available, and then the navigation tree, right? All the results can be viewed here, and all the designs what we are doing here will be updated here, right? So this CSC software is available for the students as a free of cost, as a student edition. You can directly download from the CST website, so which is a very useful thing for the students. So you can able to easily learn a software which is used to design any RF related or any frequency related circuits and designs, right? So here we can able to view, that is the home, a home will be there. So in that home you can able to view various tabs. Here you can, if you want to change the dimension, you can directly change the dimensions here, and then as the solvers can be set up here, and then this simulation can be done, and optimization and parameter sweep will be available. You can able to use in order to optimize and parameter, in order to optimize your antenna design, or in order to view the effect of any parameter on your design, right? And then the modeling, using this tab only we are going to model the entire design. So, and then post processing, the SAR, thermal losses, all the gain and directivity can be viewed here, and this is just a view, we can able to view options. So right, and here you can have a tab like the perspective view. So in this perspective view we can able to have a 3-dimensional view, so keep it in front. So in the view, it is a working plane, so this working plane can be can be disabled, and bounding box which can also be disabled. So this bounding box is nothing but the air box. So this air box is going to find out the near field values from the antenna design, and then using the Fourier transform it converts the it calculates the far field results. Right. So the first step is we have to include the parameter values. So the parameter values are these are the parameters and these are the parameters values. We have to include these parameters inside the design window, right? So WS and LS is 20 and 34. So just WS 20, LS 34. WPLP 18 and 19, WP 18, LP 19, and then W1 L1 15 and 16, W1 15, L1 16, and then WF LF 2.2 12.5, WF 2.2, LF 12.5, LG WG 8 and 20, LG 8, WG 20, and R1 and R2 is 6.5 and 5.9, R1 6.5, R2 5.9, DNS is 0.3, this is 0.3, T and H is 0.035, H is 1.6. So these are the parameters we have included. Just save, similar to, we have a save option here. Just save it here, anything. After saving, you can able to see the name has been changed, right? So the first step, we are going to design antenna A, right? And this is antenna A back, and this is antenna A front view. This is the front view and this is the back view. So this is the design, this is the final design. So both the designs are one and the same. Here, the instead of having the ground of length LG, the entire substrate, for the entire substrate length, we are going to have the ground, right? So for each value, we have to, for each value, that is for each designing, for designing an antenna, you have to design a ground, substrate, feed line and patch. For designing these 4 things, you have to give 6 values, that is the x minimum, x maximum, y minimum, y maximum, z minimum and z maximum. That is this region, x minimum, x maximum and y minimum, y maximum and z minimum and z maximum. So this is the axis, x, y and z. X in always in x direction, it is equal to the width. X represents width, y represents length and z represents height, right? So the first thing what we are going to design is, we are going to design the ground. So for designing a ground, click on this. So click on this. So we have a modeling here. So after home we have a modeling, and here you can able to view a brick. So click on this brick and again click on this working plane, press escape. On pressing this escape, then automatically it becomes a window has been popped up. So you have to replace the name as ground. So here you can able to view 6 values, x minimum, x maximum, y minimum, y maximum, z minimum and z maximum. Similarly for substrate, for patch and for feed, we have to give this 6 values. So in x we have width, and in y we have length, and in z we have the thickness, right? So what is x? So this is the x direction. So what is the length of the ground? It is equal to the length of the substrate, right? So length of the ground and length of the substrate are one and the same. So when you are going to divide with it in a straight line, then the ws, the total and ws will be equal to ws by 2 and ws by 2. So let us consider this as 0 line, then automatically this n will be equal to minus ws by 2 and this n will be equal to plus ws by 2. Then the x minimum value will be equal to minus ws by 2 and x maximum value will be plus ws by 2. So you have to rewrite it as w x minimum as ws by 2 minus ws by 2 and plus ws by 2. And similarly, what is the length? So what is the length? So length is, so in antenna A, the entire substrate is covered with the ground, so automatically the total length is ls, and again when you are going to divide it, automatically it is at the top it will be plus ls by 2, at the bottom minus ls by 2, then automatically y minimum will be minus ls by 2 plus y maximum will be plus ls by 2, and again you just replace it as minus ls by 2 plus ls by 2, and then z minimum. So z minimum will be always equal to 0, since at the lowermost bottom we are going to design the ground, and from z max the total z max will be equal to that is the thickness. Is it in the z direction we are going to have the thickness, then we have to give the thickness of the ground. The usually ground is made up of a copper. The copper thickness what we have clearly mentioned here is T. So 0 to T, and the material we used to the used for the ground is copper. So here you can load from material library. Click on that. Material library window will be popular. You can scroll down and you can able to find out the copper annealing. So load that. So you have a preview option. You can able to preview that and click on OK. So here we have designed the ground. And next step what we are going to design is we have to create a substrate, and again click on the brick and click on the working plane and escape and rename it as substrate. So for the substrate also, length width will be ws and length will be ls. Then automatically x minimum will be minus ws by 2, x maximum will be plus ws by 2, y minimum will be minus ls by 2, y maximum will be plus ls by 2, right? So here minus ws by 2 plus ws by 2 minus ls by 2 plus ls by 2, right? What is the Z minimum? So Z minimum is nothing but the from the top of the ground, that is the top of the ground is nothing but the Z maximum of the ground. From that point only we have to have the substrate. Then automatically Z minimum of the substrate will be equal to the Z maximum of the ground. So Z maximum of the ground is T. Therefore Z minimum will be equal to Z minimum of the substrate will be equal to T. And then Z maximum. So Z maximum is nothing but the substrate height. So we already know that the substrate height is h. So the Z maximum will be T plus h. And the material used is FR4. Again load from material library. So go to material library and search for the FR4, and here you can able to see FR4 lossy. Load it and click on preview. You can able to see the previews. Click on OK, and you can view that the substrate is here. When you rotate, able to rotate here you have a icon called rotate mode. Just rotate and you can zoom in and find out whether the ground is available or not. Here you can able to clearly see ground is at the bottom of the substrate. And next part is we have to design the feed line. Here you can be able to view the feed line, and the feed line is starting from minus ls by 2. So this is the bottommost layer. From minus ls by 2 up to lf, it is going to have the feed length, and feed width is wf. Again we are going to split it into 2. Then it is equal to x minimum will be equal to minus wf by 2 and x maximum will be plus wf by 2. And here you can able to see that the width of the feed is starting from minus ls by 2 line up to lf. Then automatically y minimum will be equal to minus ls by 2 and y maximum will be equal to minus ls by 2 plus lf, right? And again you just go to click on brick, click on this working plane, escape, rename it as feed. X minimum will be minus wf by 2 to plus wf by 2, and y minimum will be minus ls by 2 to minus ls by 2 plus lf, right? And what is the Z minimum and Z maximum? So Z minimum of the feed should be equal to Z minimum of the Z maximum of the substrate. So Z maximum will be T plus H, and again it is going to be the copper. Then automatically T plus H plus T will be the thickness of the Z maximum of the feed line. And you already know that the feed is made up of copper. Just click on copper and preview. You can able to view that the copper is the feed line is available. And next we are going to design the patch. Then next we are going to design the patch. This is the patch. So what is the patch length? So here you can able to see the patch width is WP and patch length is LP. So WP, when we are going to divide into 2, minus WP by 2, 2 plus WP by 2. So Z minimum will be minus WP by 2, Z maximum will be plus WP by 2, and Y minimum will be, we know that the patch is at the Y maximum of the field line. So Y maximum of the field line is minus LS by 2 plus LF. That is the Y maximum of the field line. So which is equal to the Y minimum of the patch. So from that it is up to LP, right? So automatically Y minimum will be minus LS by 2 plus LF, and Y maximum will be minus LS by 2 plus LF plus LP. And again you go back here and just click on the brick, click on escape, rename it as radiating element or radiating patch. So minus WP by 2, 2 plus WP by 2, and minus LS by 2 plus LF, minus LS by 2 plus LF plus LP. And Z minimum and Z maximum will be equal to T plus H, T plus H plus T. Similar to a field line, since at the top of the substrate only we are going to have the patch similar to field line in the same plane, so we are going to choose this. So just preview it, you can able to view the radiating element, click on OK. So in this way we have to design a radiating microstrip patch antenna. So here you can able to see that the ground is available at the bottom and there is a substrate, and then at the top of the substrate you can able to view the entire field line and the patch. So in this way we have designed, right? And the next and foremost step is we have to give the feed point. So this feed point, the feed point is the most important thing. We have to correctly give the feed point. The simplest method I will show you. So just zoom in like this, that is the thickness of the feed line is viewed on your screen. Just zoom in and click on the pick, that which is available in the modeling tab. Click on pick. You have to place this cursor like this, that is not like this or not like this. The entire thickness of the field line should be marked as red, and after that double click on that feed point. So when you are going to double click on it, then automatically it can able to, you can able to view it, or then automatically you can able to identify that the entire thickness of the feed line is changed into red dotted line. So you have chosen the point where the feed has to be placed, and then just go to home, click on macros, click on solver, ports, calculate port extension coefficient, click on that. Then automatically you can able to view the default one will be microstrip. Then click on calculate tab and click on construct port from fixed phase and close. Then automatically you can able to view that the port is fixed here, right. So you have completed a design, and you also assign the port for that. You can able to clearly see that. And next step is you have to set up your solver. Just click on setup solver, which is available in home. Click on normalize to fixed impedance of 50 ohms. Just start. Click on start. So after starting, you can able to view in the progress field that there is a progress here. You can able to clearly see the progress. So in the message box, after completion of the progress, in the message box you will be viewed the what are the different messages. So here you can able to see the passes and the delta values, line impedance values. So in the navigation you can able to see our designed values, design details. So here we have designed the ground, substrate, feed and the radiating element. So these are the things. So this is the zoom in option. You can able to zoom in and zoom out, and this symbol is activate pan mode. So when you are going to click it, you can move the entire screen. You can able to move it. And this is rotate mode. We can able to view, rotate and view the entire screen. And this is the rotate plane mode. So this is plan mode and this is plane mode. This simulation will take some time. So in the next step, what we are going to do, we are going to reduce the ground height to LG. Up to LG only we are going to reduce, and again we are going to view the output. So I think the simulation has ended. Right. So here you can able to view the 1D results. So one dimensional result. The first result what we are going to see is the S parameter. So this is the S parameter value. So you can clearly able to see below 10 dB line there is two bands which is operated at 8.61 gigahertz, and another one is have two resonating bands at 7.5 and 7.21 gigahertz. So these are some of the it is a dual band antenna we have designed with bands with the resonating band at 7.2186 and 8.614 gigahertz and 7.52 gigahertz, right? So next step what we are going to do is we are going to create a new tree folder here in the S11 as S11 comparison, since we have to compare this result after changing my design. So when I change my design, when I change any of this design values, then automatically this simulated results, all the simulated results gets disappear, right? So in order to have a copy, I just copied this result and place it here. And next step what we are going to do is we have to reduce the antenna ground length. We are going to reduce the antenna ground length. Instead of having a full ground, we are going to have the ground as LG, of length LG. So here you can go to ground directly. On double clicking on ground, you can able to, a window will be pop up, define brick, which you already defined. Click on edit. So the ground parameters will be available. Here you have to choose the y minimum value. Here the y minimum value is equal to minus ls by 2, but the y maximum value has to be changed. Instead of plus ls by 2, it has to change from minus ls by 2 to plus lg. Just replace it by minus ls by 2 plus lg. Click on preview, then you can able to view that. Click OK. So on clicking it, your ground is reduced. You can see at the bottom, you can able to clearly see the ground is reduced. Instead of having a full ground, the ground is reduced, and you can also clearly able to see that the simulated, only the copied S11 is available and the simulated results has been disappeared. So and again you go to home, then the ground, any design, in the design whenever any parameters has been changed, the ports will not change, right? So you can just go there and start simulation. Click on start simulation. It also takes some time. So in the meantime, I will show some of the results. So this is one of the my research paper here. A tree shaped. It is a three stage evaluation antenna. Here a tree shaped antenna has been designed. So with the different ground structure. In the second stage, I have included two X-shaped slots. And each stage, third stage, it is a metamaterial has been included, and these are the dimensions of that. So here you can able to view that antenna A, which is resonating at a wide band from nearly 3 to 8.5 gigahertz, and antenna B, that is by introducing a X-shaped slot, it is operating at 5.8, nearly 5.8 gigahertz, and antenna C, after including a metamaterial, it is having a resonance at 4.8 gigahertz also. So an additional, the wideband has been converted into narrowband at the application oriented. And this is another design antenna. Here also I am going to have 6 stages of evaluation. The first stage, a simple microstrip offset feed, and then the design complementary splitting resonators, and splitting resonators has been introduced at the end, and I can able to achieve 8 number of bands. This is another output, and this is the metamaterial structure. So here after introduction of a splitting resonator, I can able to achieve multiple bands, and this is the for the radar. Co-directional CSRR has been used, and here you can able to view it can be operated from 25 gigahertz to 31 nearly 30 gigahertz. So this is for the short range radar. So these are some of the research details, right? I think the simulation has been completed, so you can able to view the output of the navigation tree. So here again the S parameter has been given, has been obtained, and you can able to view, just click and drag it. You can able to view that this is antenna A, that is full ground, and with the defective ground structure I can able to achieve 5.2 gigahertz, right? So which is a wireless application, and here also I can able to nearly achieve a output here nearly 2.5 gigahertz. Also I have a slightly below a good return loss has been obtained. So here you can able to view, which is the resonant frequency is 5.3 gigahertz, and the return loss value is equal to 34.17, and the bandwidth of this band will be equal to, from the band operating band is from 3.71 gigahertz to 6.26 gigahertz, and the bandwidth will be equal to 2.54 gigahertz. So this is antenna number 2. And next one is we are going to introduce a slot. We are going to introduce a slot like this of length W1 and L1, right? W1 and L1. So this W1, when you are going to divide it into W1 minus W1 by 2, 2 plus W1 by 2, X minimum will be minus W1 by 2, X maximum will be plus W1 by 2, and Y minimum will be equal to, from the top it is L1, then automatically Y minimum, I am going to choose the Y minimum as top and Y maximum as this. So from the top means minus LS by 2 plus LF plus LP, and Y maximum will be minus L1, right? So just go to modeling, click on brick, click right, click escape. So rename it as slot minus W1 by 2 to plus W1 by 2 minus ls by 2 plus lf plus lp minus ls by 2 plus lf plus lp minus l1, and maximum will be t plus h, t plus h plus t. This Z minimum and Z maximum should be equal to the value from which the slot has to be etched, and usually the material used should be vacuum in order to etch the part. And click on preview, you can able to preview that there is a slot. Click on OK. So here the radiating element is there and the slot is available. From the radiating element you have to etch this slot. So click on radiating element, click on boolean, add subtract, click on subtract and click on slot and press enter. So like this you can create a slot. And next step what we are going to do is we have to introduce two rings like this. So I am going to choose two rings, one is from R1 and second one is R2, and D and S be the thickness. So I am going to choose ring, click on this ring cylinder and press escape. The outer ring is R1 and the inner ring is R1 minus S, and let us consider Y center as 4.5 and same thickness. Material, and in order to have a ring, segment as 1000, and you can able to have a ring. Click on OK. And another ring, click on R2, R2 minus D, 3.5, T plus H, T plus H plus T, 1000 and preview. Click on OK. You can able to view that there are two rings available here, and then you have to have a split like this. So click on brick, escape. So that is a split here. You have a split here, co-direction split. So click on brick, escape. And the width of the split is equal to D. So D by 2, sorry, minus D by 2 plus D by 2 and 8 to 12, T plus H, T plus H plus T. And in order to etch back, you have to use vacuum. Here you can able to see that. Click on OK. Click OK. So just add radiating patch with and two rings. So it takes some time. So here you can able to see that the radiating two rings has been joined with the radiating element, and here it is the, now you have to separate that slot here, and you can able to see that the slot is created at the ring, and this is the final ring structure. And then you just start the simulation. And again the simulation has been taking place, and you can able to clearly view the outputs. So this is the final stage of the microstrip patch antenna. So in this way only we have to design a microstrip patch antenna, which can be easily done with the CST Studio when compared with the other simulation softwares. So the all the simulation softwares will give the same output approximately equal to each other. So CST now is widely used because of its user friendly nature, and this is the final output. So I think still it will take some time, since the design becomes more complex. The design becomes more complex, the time taken will be quite high. Right, so this is my YouTube channel. So in this channel you can able to view all my design samples. So this is the this YouTube channel has started now, so which is every week we are going to upload a new video. So you can subscribe that and click on the notification, so that you can have a notification whenever you are going to whenever I am going to upload a video. So it will be useful for you. So we plan to organize similar workshops, free webinars in future also. So this is my mail ID. You can mail any of your queries, and this is my WhatsApp number. So you can note down and give you can chat any queries. You can give your queries, so that I can answer you. So it will take some time. So in the parameters, you can give all the parameters you can able to define here, and also you can write an equation to calculate the parameters here. So this is the navigation tree. So in the navigation tree you can able to view all the outputs, the two-dimensional outputs, far field results, tables, PLM results. So because of the lack of time I cannot able to show you all the other results. Just I have given an insight about the design procedure, and how to find out the return loss and bandwidth and other and the resonant frequency of the antenna. So in my future videos and some other videos is already available in my channel. You can view that, and so that you can able to view what are the other result and how to analyze that result can be easily understandable. So I have given that links in my channel. And next one is when you are going to make use of a metamaterial. So you have to place that metamaterial at the place where your surface current is maximum, right? So first you have to design your antenna and you have to analyze your surface current. So after analyzing your surface current, you can able to find out the maximum surface current area at your region. So if the surface current is maximum in that region, so in this region, then you have to place the designed metamaterial in this region. Otherwise the metamaterial will not work. So you have to just design the simple patch and a microstrip patch, and you have to analyze the surface current, and then you have to design a metamaterial and place that metamaterial where the maximum surface current is available. You can able to easily identify the maximum surface current, and then you have to place the metamaterial there. So it will take some time. So in the chat box I will send the feedback. In the chat box itself I will upload the feedback link. So you can click on the feedback link and give me the feedback about the webinar, so that I can able to improve my webinar in the future also. I will upload the feedback link by 6:30, and the feedback response, kindly update your feedback response within 6:45, and after 6:45 the link will be disabled. The members who completed the feedback only will receive the e-certificates, others do not receive, since it is YouTube live, anyone can able to view. So only the members who are going to complete the feedback will receive the e-certificates. If you have any queries regarding the antenna design or any other microwave devices, you can able to contact me. I have given my number, and I think the simulation has been completed. So, and again you can go back there and click on S11 parameter and just choose it here. You can able to view. So this is antenna number 1, that is with full ground, and this is with off ground, and another one is with a metamaterial. You can clearly able to see a new band has been created here, and another band, a dual band, has been created with the help of a metamaterial, right? The same frequency with some reduction in the return loss has been available. So this is how you have to design. In my future webinars I will able to show you how to calculate the surface current, all the other related parameters to the antenna measurements. So hope this webinar will be useful for you, and thank you for your patient listening. So, and again I will show my contacts. Antenna design using CST software, Prasad Jones. This is my YouTube channel. You can subscribe on that, and you can get help from that. And this is my mail ID, and this is my phone number, right? So thank you very much for your patient listening. Thank you. And by 6:30 I will upload the feedback form link in the same chat box. You can able to view that. By 6:45 it will be closed. So kindly update your feedback before 6:45, and thank you very much.